Welcome to Module 2 of Plant Design and Economics. This is Lecture 6. In this week, we will talk about selection of process equipment, utilities, plant location and layout. Today is the first lecture of Module 2, and in this lecture, we will talk about how to select process equipment. So, this is today's topic: selection of process equipment, materials of construction and equipment specification. What you see is a schematic of a typical chemical process represented in terms of functional blocks. So, first block represents raw material storage, then feed preparation. Feed goes to reactor for reaction, then the effluents from the reactor goes to product separation. Part of separated products is recycled back, the unreacted material is recycled back, the byproducts are taken out and the sellable byproducts are sent for sales. The product is purified, the waste goes to pollution control, and the purified product is stored for sales. So, what you see is a chemical engineering process is an assembly of several units. Each unit performs a specific operation. Plant design is concerned with the selection, specification and design of equipment so that each unit can perform specified functions. Once you have prepared the flow sheet diagram, the logical step after that will be the selection of process equipment and suitable materials of construction for all parts of the plant. For construction of plant, we need detailed design specifications and fabrication drawings for all equipment including instruments, wiring, piping and auxiliaries. So, we need to have very detailed design specifications for all equipment and auxiliaries. Now, experience tells us that very few new ideas about processes ever actually materialize. According to James Douglas, this number is less than 1%. So, you can well imagine that money spent to design such discarded proposals is lost forever. Thus, we have to quickly identify appropriate equipment cost so that the economic promise of future efforts can be predicted. So, that will tell us whether to go ahead with the new proposal or not. Shortcut design techniques are used to obtain inexpensive answers with reasonable accuracy. Remember that shortcut designs are no substitute for more rigorous designs required to actually build equipment. Shortcut designs are adequate for the purpose of cost estimation. In the very beginning of your selection of equipment, you need to decide whether the plant will be built as a single train or dual train when you are going to design a continuous process. A single train plant means that there is no duplication of units. There is a single sequence of units and all the materials go through each unit. It is low cost to build, but you can imagine that failure of any item in the plant will cause the shutdown of the entire plant. For dual trains, there will be two identical plants built side by side, and half the flow will go through each. It will be something like two trains in parallel. So, obviously, it will be more expensive to build, but one unit will remain operative if the other one unit fails. So, that is an advantage. So, this advantage comes with higher cost. To avoid unplanned shutdown, many items, particularly valves, control valves, are purchased as spares and are often installed in parallel with the operating ones. Now, when you are going to select process equipments, a question will arise whether to buy the equipment or build the equipment. Both the roles are played by engineers. Engineers are buyers of equipment, engineers are builders of equipment as well. Imagine a case, you wish to acquire an automobile. You have two options. You can build a car from scratch, or you can buy a car made by specialist manufacturer. What we will do will depend on which company you work with. For example, if you are working with an automobile company and you are in the charge of designing a car, you will build the car from scratch. Otherwise, you can buy a car made by specialist manufacturer. In both the cases, experience and judgment are valuable, but the levels of expertise and detailed knowledge required are very, very different. Now, let us be familiar with certain terminology. Cookers, coolers, economizers, kettles, preheaters, reboilers, superheaters, thermosiphons, all are heat exchangers, and they are often identical in designs. Fume collection, stripping, scrubbing, humidification, fractionation, all are carried out in packed towers or tray towers. And these towers you know as distillation columns or absorption columns, as you have studied in mass transfer courses. A large number of chemical process equipment found in chemical engineering catalogs can be combined into a smaller set of generic groups. These groups, for example, may be evaporators, vaporizer, conveyors, crushers, millers, grinders, furnaces, gas movers, compressors, gas solid contacting equipment, heat exchangers, mixers, etc. So, there may be several equipment which are used in industry like coolers, heaters, furnaces, etc., all may come under heat exchangers. Furnaces will put separately, but you have coolers, you have heaters, you have economizers, etc., as you have seen in our previous slides. Now, it is important to be familiar with these generic groups as well as the equipments that come under these generic groups. Then it will be easier for us when you select a particular piece of equipment for our purpose. The other set of groups: process vessels, pumps, reactors, separators, size enlargement equipment, storage vessels. Now, broadly, there are two types of equipments that are used in chemical process industries. We call them proprietary equipment and non-proprietary equipment. Proprietary equipment are designed and manufactured by specialist manufacturers and sold as standard catalog items. For example, pumps, compressors, filters, centrifuges, dryers, etc. Whereas non-proprietary equipment are designed specifically for particular process. These are custom built for a company by specialist fabricators. Examples are reactors, distillation columns, heat exchangers, etc. So, proprietary items are like standard equipment, whereas non-proprietary equipment are special equipment. So, if you are not working with automobile company who is in charge of designing a car, you will buy proprietary equipment. If you are not working with specialist equipment manufacturers, a chemical engineer is not normally involved in the detailed design of proprietary equipment. So, again with the analogy of that building a car or buying a car, if you are not working with automobile company who will design a car, you will buy from the standard manufacturer of the car. So, a chemical engineer who is not working with equipment manufacturers will not normally be involved in the detailed design of proprietary equipment, because the proprietary equipment are standard equipment and you can buy it as off the shelf item. It is like you go to market and buy a piece of equipment. So, if you are not working with a company who manufactures equipment, then what will be your role as chemical engineer for selecting proprietary equipment? You have to specify the process duty such as temperature, pressure, flow rate, etc., and select the appropriate equipment needed for the particular process. Proprietary items are generally available in certain standard sizes. So, you have to decide on which size will be most suitable for your process. Perhaps you need to consult with the supplier of that proprietary equipment for this purpose. You may also have to think whether any modification of standard equipment is necessary for the particular application you have in hand. For example, a standard tunnel dryer which has been designed to handle particulate solids may be adapted to dry synthetic fibers. So, you have to talk to the vendor or the supplier of the equipment whether there is any scope for such adaptation or modification of standard equipment, so that it will be useful for your particular application in hand. Remember, use of standard off the shelf equipment will always reduce the cost. For non-proprietary equipment, the role of chemical engineers will be selection and sizing of the equipment. You have to develop detailed design data giving sizes, operating conditions, number and location of openings, types of flanges and heads, variation allowances and other information. For example, For construction of a distillation column, you have to determine the number of plates, the types of plates, the design of plates, the diameter of the column, the position of inlet nozzle, outlet nozzle and instrument nozzles. You have to specify the basic control loops. This information is then supplied in the form of sketches and specification sheets to the specialist mechanical design groups of an engineering, procurement and construction company for detailed design. Engineering, procurement and construction company, which are known as EPC company, will take the specification from you and will perform detailed design. There are several such companies. Some of the popular companies you may be familiar with are Engineers India Limited, L&T, ABB, Bechtel, etc. Remember again, whenever possible, standard specifications should be used. The common basis for design is past experience and accurate data that are available in the literature. Now, for the particular design you have in hand, if the above two things like past experience as well as data available in the literature are not adequate, then it may be necessary to perform pilot plant tests. So, pilot plant tests may be necessary to design effective plant equipment when you do not have past experience or you do not have adequate past experience or you do not have accurate data available in literature. So, the results of the pilot plant test must be scaled up to the plant capacity. But remember, the pilot plant test will not be necessary for design of every piece of equipment. We will shortly see the cases where pilot plant testing are always necessary and the cases where they are not necessary always. A chemical engineer should be acquainted with the limitations of scale-up methods and should know how to select the essential design variables. So, this table shows some of the equipment when it is always necessary to perform pilot test for the purpose of design of those equipment. For example, batch reactor, continuous reactor, crystallizer, rotary filters, plate and frame filters, etc. The table also shows the major variables for operational design, major variables characterizing size or capacity, and also maximum scale-up ratio. For example, the major variables for operational design for continuous reactor will be reaction rate and equilibrium state. The major variables characterizing size or capacity for continuous reactors will be flow rate and residence time. The maximum scale-up ratio is 100:1. This table tells you that for these equipment, the pilot plant test is always not necessary. So, centrifugal pumps, L&T heat exchanger, plate columns, spray columns, for these equipment, you do not need to perform pilot plant test. The table also gives you major variables for operational design, major variables characterizing size or capacity as well as maximum scale-up ratio. So, you see that batch reactor, continuous reactor, crystallizer, all types of filters For them, pilot plant test is necessary, whereas equipment like centrifugal pump, selective heat exchanger, PET columns, spray columns, pilot plant test is not necessary. This list is of course not exhaustive, so you need to consult textbooks for exhaustive lists. Now, while selecting equipment, a reasonable safety factor for selection and design of equipment should be applied. Safety factors represent the amount of over-design that would be used to account for the changes in the operating performance with time and the uncertainties in the design process that will always be there due to uncertainty in data, due to uncertainty in the calculation process. Remember, the indiscriminate application of safety factors should be avoided. So, too much of over design must be avoided. Otherwise, the process or equipment would never prove its economic value. Some typical safety factors are given here: batch reactor 20%, continuous reactor 20%, crystallizer 20%, cyclone 10%, plate columns 15%, cell and tube, heat exchanger 15%, reciprocating compressor 10%, so on and so forth. So, typically the safety factors lie between 10 to 20%. Generally, the magnitudes of safety factors are determined by economic or market considerations, accuracy of the design data and calculations, potential changes in the operating conditions, background information available on the overall process, amount of safety factors used in other components of the design. Now, let us talk little more about standard versus special process equipment. We have talked about proprietary equipment and non-proprietary equipment. Proprietary equipment are standard equipment, non-proprietary equipment are special equipment. As we have told again and again, standard equipment should be selected whenever possible. Standard equipment has stood the rigorous test of service. A new design, thus a special equipment, is a new experiment for both user and designer. So, there may be uncertainty involved in the performance. So, if possible, we should always use standard equipment that can be purchased off the shelf from specialist manufacturers. The use of standard equipment reduces the cost. If you use standard equipment, the duplication will be easy. The manufacturers may have the desired size in stock. Better guarantee of satisfactory performance may be obtained for standard equipment because the supplier has confidence in the design which has been matured over a longer period of time. Also, standard equipments are easy to repair. Now, about process equipment specifications. Before an equipment manufacturer is contacted, the chemical engineer should prepare a preliminary specification sheet for the equipment. The following information must be included in the specification sheet so that the cost of purchasing and installing each piece of equipment can be determined. Specific type of equipment, size and or capacity, material of construction, operating pressure, maximum operating temperature when the operating temperature is above ambient, minimum operating temperature when the operating temperature is below ambient or maybe under refrigerated conditions, essential controls, insulation required, corrosion allowances if it is large, special features such as jackets on heat exchangers, duplication of plant items for safety and or reliability, delivery date, support, etc. So, all this information must be included in the specification sheet. Now, the heat exchangers and pumps cannot be sized until the energy balance for the plant is completed. The final energy balance depends upon the energy conservation measure to be employed and the plant layout. That means, the final energy balance will depend on the energy integration that you are going to adopt for your plant as well as on the plant layout. But all other equipments can be sized reasonably accurately at this stage. There are many approximate methods of equipment sizings available in textbooks. We will take a small example here. Let us size a methanol storage tank for a plant which produces 10,000 tons of a particular product per year. Given 0.3 kg of methanol is required for each kg of product, a 15-day storage capacity is specified for methanol. The plant will operate 8,300 hours per year. So, how do I size the methanol storage tank? Now, let us use our process calculation principles. So, kg of methanol used per day can be obtained as 0.3 kg methanol per kg product multiplied by 10,000 tons of product per year. Then you have 8,300 hours in a year and you have 24 hours in a day. So, if you multiply these quantities, you get kg of methanol used per day as 8,675. So, 8,675 kg of methanol will be used per day. Now, the amount of methanol that must be stored over 15 days can be found out simply by multiplying with 15. So, that gives me 130 into 10 to the power 3 kg of methanol. So, the volume of methanol that must be stored can be obtained by dividing this quantity with the density of methanol, which is 792 kg per meter cube. So, I get 165 meter cube volume of methanol that must be stored. Now, let us assume the length of storage tank is 3 times the diameter. So, L by D is 3 and it will only be filled to a maximum 90% of the capacity. So, then size of the tank can be easily obtained. So, pi d square by 4 into L, which when you put L by D equal to 3 will be 3 pi d cube by 4. So, this quantity will be equated to 165 by 0.90. So, the diameter of the tank can be obtained as 4.27 meter and L can be obtained as 3 times of it, which is 12.81 meter. So, this is how you can design, you can size the tank. So, this is a typical example of specification sheet for heat exchanger. another specification sheet for distillation column. Now, let us quickly talk about materials of construction for process equipment. A good understanding of the process and all process related information is required for selecting materials of construction. Final choice of raw materials must be made first before you try to select the materials of construction. Consider the effects of corrosion and erosion, perform laboratory testing if necessary. The materials of construction should have good chemical resistance. It should be resistant to the corrosive action of any chemicals that may contact the exposed surfaces. The materials of construction should have good structural strength, resistance to physical or thermal shock, favorable cost, ease of fabrication and maintenance. So, here are certain guidelines for selection of materials of construction. Preliminary selection can be done based on experience, manufacturer's data, literature, availability, laboratory testing. Then properties, mechanical and physical properties, tensile strength, stiffness, toughness, hardness, fatigue resistance, corrosion, erosion resistance. Now, after doing preliminary selection, you perhaps will select a set of equipment, a set of materials of construction which are probable candidates, then this will go final screening. So, final selection will be based on both technical factors as well as economic factors. Fabrication method, effect of temperature, pressure, agitation, possibility of impurity, material cost, production cost, probable life of equipment, product degradation, liability of special hazards, etc. So, these are the factors which you can use as guidelines for selection of materials of construction. So, with this we will stop our discussion on selection of process equipment. Thank you for watching.